Welcome to the next video on linear models. This is video 5 on multivariate normal distributions, and it is the start of chapter 1, section 2. So let's start from a definition. So imagine that we have some n random vectors, each of them independent and distributed as a normal distribution with mean equal to 0 and variance 1. So this is an independent identical distribution, right? Identically distributed random variables. And we form them into a column vector. And then suppose that we have any constant matrix A and constant vector B appropriately shaped so that the matrix product and the vector sum all make sense here, so they have the right dimensions. Then we call this thing, this vector y, is called a multivariate normal distribution. Now, when that is the case, we will write that y is distributed with, this notation indicating its mean and its covariance. And by the way, right, of course, when you take the expected value of this, then this all turns into 0, and you're left only with b, so that's why the expected value of such a thing is b, and that's why we put b right there. Also, if you take the covariance of this thing, the covariance will kill any constant vector so that b goes away. Then you're taking the covariance of this. That'll get you A covariance z times A transpose. And so, maybe I'll go ahead and indicate that this turns into cov z, but with A over here and A transpose over here. And the idea is that this covariance of z, where is that? What is that? Well, remember, these are, right, all the random variables in it are independent. So when we draw out this matrix, everything below and above the main diagonal is going to be 0 because of the independence assumption. And then when you think about the values along the main diagonal, those are the variances of each individual random variable. And since we assume that that is equal to 1, then you get 1s along the main diagonal. And what that means is that that matrix in the middle is the identity matrix and just goes away, and you're left with A transpose. So that's why we write that right here. Now, an important point that is going to take up the rest of this video is that if you know the matrix A and the vector B, then, sort of the vector y is completely determined. We know what this thing is, so to speak. But the other way around, the converse is not true. If I were to give you this and ask you what is the corresponding, vector z, or what is the corresponding matrix A. And in particular, to kind of drive the point home, imagine that it was instead given to you, as mu v, right? So v presumably is somehow the result of computing A prime, but you don't get to see the matrix A, right? So you see the matrix V, and you are sort of told or promised that it comes as the result of some matrix A times A transpose. But then you're asked, what is the matrix A, right? Well, it turns out that there are examples where, and this is kind of pathological, right? So it's not just weird examples, but there are plenty of examples where there are multiple correct answers to that question, right? So in some cases, you'll be able to find a matrix A so that the matrix V is A prime, but also you'll find another matrix B where the matrix V is also equal to B prime, right? So basically the sort of worrying thing is that if I were to give you this, right, and you had to backtrack and figure out what that matrix A is, you couldn't do it. It's not possible because there's more than one correct answer. And then what that at least seems like it risks is that there might be more than one correct y, right? Because after all, y is based on what that matrix A is. So if you get it wrong and you think that it's matrix B because that's also a solution to this equation, then you might think that y is equal to this over here. So that sounds like a risk, right? It sounds like we should never specify that something is distributed like this, because then you won't actually know what is the distribution of the random variable, right? You won't know, is it this one or is it this one? Well, the next theorem is going to tell us that actually that's not a worry. No matter what the matrix no matter what matrix you pick, right? So long as it comes out to the same, matrix that we've been calling V, then the vector y will always be distributed the same way, right? So that effectively, what you really care about, which is the distribution of y, is not affected by which matrix we use here. If it's A or B, all that matters is that the product here comes out to the right matrix. So we're going to prove that in this theorem. So suppose that you have some two random vectors and they have the same normal distribution here. They have the same parameters within this expression, right? They have the same mu. I guess out of consistency, I had to say mu with an arrow on it because it's a vector. But anyway, so they have the same mu and the same v. But that's all we're guaranteed, right? We don't know whether that V corresponds to a matrix AA prime or a matrix BB prime. Okay. What we are going to prove is that Y and W nonetheless must still have the same distribution. How are we going to prove it? Well, from mathematical statistics, I think we're all kind of familiar with proving that some two random variables have the same distribution if they have the same moment generating function. So this is a very useful property that you can use to basically take some two random variables, compute their moment generating function, show that the functions are equal, and that allows you to infer that therefore the random variables that they came from must have the same distribution. So that's a very useful technique in proving that some two things have the same distribution. It turns out that there is a similar thing called the characteristic function. And if you look at the characteristic function on a first glance, it might even look a little bit like the moment generating function. But there is a big difference, and it is the presence of this I, this complex number I. We are talking about taking the expected value of the exponential of itx. And by the way, this is a function of t. I might as well emphasize that while I'm thinking about it, that for each t you get a different value, right? A different value of this expectation. So t is the variable of this function, right? Tell me a t, I'm going to compute an expectation. But the problem here is that this is a complex number, right? This is a complex valued random variable, and I find this kind of frustrating and kind of unfair when something so unusual, like I think most people who would read this book or take this class would never have encountered might not have encountered complex numbers for quite a while, and then wouldn't have ever seen the expected value of a complex random variable, and also wouldn't have seen this before. So to just throw it out there and start using it in a proof the way that the book does, I find, just feels unfair, right? It feels like we were told that the prerequisites were relatively small, and suddenly we're getting hit with a pretty long story that's not even in the book, and it's just kind of assumed that we're comfortable with this. So not my favorite thing. But all of that said, for all of my belly aching, I am in fact going to just charge forward and not even try to explain this stuff, because it would just kind of take us far from our interests. But in any case, so I'm going to just move on, and we're just going to not even think too hard about what the hell is going on here. So we're just going to sort of take it for granted that if some two things have the same characteristic function, right? The strategy, by the way, is going to be exactly the same as with the moment generating function. So we're going to say that if you take some two random variables, and if you compute their characteristic function and those characteristic functions are the same, then the random variables must have had the same distribution. And we're just going to try to work with this thing without thinking too much about what's going on inside of it. Anyway, We will also need one other unfair thing that nobody, I think, or almost nobody taking this course could possibly have known before, and yet the book just throws it around like it's common knowledge, is that for a standard normal random variable, the characteristic function is actually the same thing as this right here, right? So it's the exponential of negative t squared over 2, blah, blah, blah. But the important point is that deriving this equality is quite hard. I believe it involves computing some like complex contour integral with, something sent out to infinity, blah, 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 if I remember correctly. So in any case, so we're not going to go into all of that, but you have to just take it on faith that these two things are equal in the case of a standard normal random variable. Okay, so with those things in hand, we can actually now do a bunch of work. So, and also we're going to take it for granted, and this is going to be a function of a vector t, right? So this is how things get generalized to our vector situation. So this is now a many variable function phi. And we are going to take it as a premise that if some two functions have the same characteristic function, even in the multivariable case, right? We're just going to take it for granted that in the multivariable case, yet again, if they share the same characteristic function, then therefore they must have the same distribution. Okay, so we're going to start from that, and that's right, that phi of t is this thing right here, right? So just we're kind of generalizing everything to the case of vectors. And so what that means is, yet again, we're going to have expected value of the expectation of I times, now here's where things get vectory. We've got the vector t transpose times the vector. We're going to talk for a minute about the vector z, although that's right. This is all just some work and computation that's going to be useful when we actually get to the main steps of the proof. But this is just a bunch of stuff that's going to be useful in a minute, so bear with me on that. Now we can make this move right away, and this is actually, right, we don't need any special knowledge for this. This is just the fact that when we're doing t prime times z, we're doing a dot product, and so the dot product is just, right, you just get, like if you think of like a matrix product for these vectors, right, and you've got a row here and a column here, then, well, this is just effectively what you get when you do the matrix product. So that's very straightforward. That's just linear algebra. Then from here, nothing terribly special is going on. It might look a little funny, but really we're taking the expected value of a sum, and we can always kind of just use the law, right, the exponent law, to turn that into a product, and that's all I'm doing here. Yes, it's generalized in like this summation notation and this product notation, but it's really no different from the basic thing that we know from high school, that these two things are equal, right? So this familiar exponent law, when generalized to longer sums and products, is just the same thing as the move from here to there. So that's not a big deal. Here is where we use exactly the thing that I prepped you for up above. So the expected value of this standard normal random variable turns into this function of t. From there, we can, again, kind of do, what we did before in reverse, right? Now we're changing a product out for a sum using, again, the exponent laws. And then from here, we're just using the fact that the sum over tj squared, right, the sum over the coordinates squared for a vector is the same thing as the vector dot product with itself. So no, right, that's just a linear algebra move, so that one seems fair to me. And so we get this result, right? And so we haven't proved what we set out to prove, but it'll be a useful tool in a minute. So let's now get down to the main proof. For the main proof, we're, this time going to look at the characteristic function, this time for y. Okay. Natural thing to do is to expand y. Y is az plus mu, and so if I just multiply in that I times T transpose, then this is what I get. Okay, then when I take the exponential for this sum, then I'm gonna, I'm gonna again use my exponent laws and break it up into a product. And especially this part right here can just kind of pop out of the expectation because it is a constant with respect to, taking this expectation, right? Because we're taking the expectation of these random variables that are in Z basically, right? So this is like a constant and can just move outside of the expectation. Now, one thing to notice here is that this right here is effectively the same thing as, clearly it's somehow like pretty close to related to a characteristic function that is relevant just to Z. So if we think about, taking that characteristic function for Z, then by definition we would, right? Like it's just imagine taking a prime t and like evaluating it there, right? So you would do the normal thing, right? You would get the expected value of the exponential of I times, and then, normally this would just be t transpose, but because we're plugging in a transpose t, then that kind of, turns into this, right? So taking the transpose of that product, you get this right here. And then, what would be nice is to then take A and group it together with Z. And when you do, you see that like we're basically talking about what we have over here. So in effect, what I'm saying is that the characteristic function for Z, if you plug in A transpose T, you get the same thing as what we got up here, right? So I'm making this connection here, okay. And from there, we can then use the fact, like what we just derived up above, right? So this right here is where I'm using the result that we derived up above to say that therefore this now turns into the exponential of negative this vector, right, this vector transpose, right? So this thing right here is like playing the role of this thing right here in the result from up above, and this thing right here is that, and there's of course the divide by 2. So, right, so that's the alignment with the result that we got from the previous part. Okay, great. Now, and I think I'm missing a transpose, so let me go ahead and make sure that I put the transpose right. There's supposed to be a transpose on that A, and the important part about all of that is that A transpose is a matrix that we're going to call V. And the important part is that A doesn't matter. If you did this all over again with the vector W, you would get exactly the same thing, based on the principle that we're kind of assuming that the matrix W is given by some BZ plus B. But the important, you're right, like the sort of assumption underneath all of this is that B transpose would also be equal to V, right? That's also equal to A transpose. And so, kind of the important point here is that whether you use A transpose, you get V, or if you use BB transpose because it's coming from W, you still get V. You get the same thing. And so at the end of the day, what we have now shown is that this characteristic function is equal to this characteristic function. One of them is for the vector y, the other one is for the vector w, and therefore they have the same characteristic function. Therefore, they are distributed the same, concluding the proof.